All right, the next comparison test is going to be called the limit comparison test. And often says this series closely resembles a p-series or geometric series, but I can't do the direct comparison test because I can't say, like, for every single term by term, one of them is always bigger than the other one. If that happens, then we can use this limit comparison test. So it's just saying, suppose that the sequence, all the terms in the sequence are greater than 0. Nothing can be 0. If that happens, then the limit of one sequence over the other sequence, if that's equal to a positive finite number, finite just meaning not infinity, and can't be negative, it's got to be positive finite number, not infinity, then either both series converge or both series diverge. So that's actually really nice. This first one, it's saying, it's something that I used a minute ago when I said the general harmonic on that first example. It's saying show that the general harmonic series diverges. So what it's saying is we know this is the harmonic series. It's a p-series with p equals 1. It diverges, period. What this is saying is anything in that form, 1 over a positive number in front of n plus a positive number, will always diverge. So it's saying show that, and we're going to use the limit comparison test with this 1 over n. So it doesn't matter which one's A, which one's B, just put one over the other one. Usually I write the limit as n goes to infinity of the original over the one we're comparing. And then this is going to be equal to the limit as n goes to infinity. I basically just, instead of dividing by 1 over n, I multiply by n over 1. So this would be n over a to the n plus b. And as n goes to infinity, I can use, I get that indeterminate form infinity over infinity, so I would do L'Hopital's rule. I'm just applying L'Hopital's rule. I don't want to actually write it out. But the limit of the top is equal to infinity, so is the bottom. So this would be equal to the limit as n goes to infinity of 1 over a. And since a is positive, 1 over a is just going to be, it doesn't matter what n is, right? It canceled out. So this just be equal to 1 over a. So that tells us, since the series that we knew this one diverges. So now I can say every single general harmonic diverges by the limit comparison test, where I just get a positive finite number here. All right, so it says when we're trying to figure out what we're going to compare with, if I've got some kind of polynomial, which is like 1 on top and something on the bottom, I'm going to compare it to just the highest exponent down there. So like the biggest degree, so just 1 over n cubed, or 1 over n squared. If I've got 1 over with a square root on the bottom, I'm just going to compare it to 1 over square root of n. Since this first one, I just kind of skipped over it. It's a p-series, the p is 2, so they both converge. And then this is a geometric series where r is, this is a p-series also. P-series, the p equals 1/2. Excuse me, side diverges. Excuse me. If I've got several different exponents on top and bottom, I'm just going to simplify that and just have compare it to 1 over n cubed. So look at the highest exponent on the top, bottom, kind of reduce that, and I would compare it to 1 over n cubed. And you'll kind of get better as we do some more practice. All right, so this one, I'm going to do the limit comparison test. And what should I compare it to? I'm going to compare it with something that we know. It's just going to be square root of n over n squared. Just looking at those highest exponents, which would, I guess I can reduce this down to be equal to n equals 1. That's n to the 1/2 on top, and then n squared on the bottom. So there'd be, 3 over 2 here. So that's a p-series with p greater than 1, so it's a converging p-series. P-series that converges. So if I find the limit as n goes to infinity I don't know what's going on with the pen. As n goes to infinity of square root n over n squared plus 1 all over, I could say square root of n over n squared. And if this gives me a positive finite number, then I know my original series also converges because they'll behave the same. So square root of n over n squared plus 1 times n squared over square root of n. And some L'Hopital's, oh no, this is some bad notation. I need to say this is equal to the limit as n goes to infinity. So I would basically kind of say the limit as n goes to infinity of, what would that be? N to the 2, so 5 over 2 over n 5 over 2 times n to the 1/2. And if you apply L'Hopital's theorem, I get 1. And since 1 is a positive finite number, this is a plus, that changes everything. Since that's a positive finite number, then I know my original series also converges by the limit comparison test. So I might say since 1 is positive and finite. All right, limit comparison test. All right, so part B, let's see. What am I going to compare this with? I've got a 2 to the power n on top. That's like the highest part on the top. And then maybe this n and this n cubed kind of like cancel out basically and just make the n on the bottom. This is n is equal to 1, 2 to the n over n squared. And I got to think, okay, is that a geometric series? No. Is it a p series? No. Could I integrate that? Ugh. But the nth term test for divergence says if the limit of this sequence is not 0, then it diverges. Or if it's not, it's not 0, it diverges. So this is infinity. That limit is infinity. So this diverges by the nth term test. So if I compare the two, and let me erase all this down. If I do the limit of their quotients, as n goes to infinity, n to the 2n over 4n cubed plus 1, all over 2 to the n over n squared. That will be equal to the limit as n goes to infinity. Do my keep, change, flip stuff. And I'm going to get, I can basically, I think, like the two thens kind of cancel each other out. This would be n squared times n cubed kind of cancels out at infinity. So my limit would be 1/4. And since 1/4 is finite and positive, I know this series also diverges by the limit comparison test. Since I'm comparing it to something that diverges, and it gave me a positive finite number when I compared the limits of the quotients, it also diverges. All right, now we just have some examples of what to do, when to do it. So I'm looking at this one. Which of the following statements about convergence of the series blank is true? Oh boy, this looks fun. Haven't done with a natural log of n before. I'm going to say this is comparing this. So this is diverges, right? So if by comparing the two, would I say one? Which one? If that one diverges, if the smaller one diverges, the bigger one diverges. But if I think about the graphs of just the denominator, so that would look like kind of like that, just a straight line. Just as I plug in one, it gets bigger. Plug in 2, it's 2. Plug in 3, it's 3. But the natural log function looks kind of like that, right? So that means this denominator is going to be smaller, making this whole number bigger. So I'm not sure I can say that one, if the smaller one diverges. Oh wait, no, that one's smaller. This one's smaller, right? The bottom is bigger, making the overall fraction smaller. The smaller one diverges, so the bigger one we can't say. All right, we're going to say that converges comparison with that. I don't want to do that. I already kind of looked at the 1 over the n diverging, right? So if 1 over n diverges and it is smaller, then the bigger one diverges. Because remember, okay, I got a bad job explaining this. If I just look at 1 over n, I looked at n being like this and then natural log. I'm just comparing the bottoms. 1 over n is going to be a bigger, or sorry, n is bigger than natural log of n. So overall, the fraction would be smaller since the denominator is bigger. So since this is smaller and it diverges, then I know the bigger one also diverges. And I'm just not going to think about those other two. All right, the next one, let's see. Consider the series a of n, b of n. A is greater than 0, so is b. If a of n diverges, which must be true? So if a of n is less than or equal to b of n converges. But we're saying this, the smaller one diverges, then the bigger one needs to diverge, right? So that's wrong. If the smaller one diverges, then the bigger one diverges. I think that might be the one. If b of n is smaller, so this is saying if the bigger one, now it's called, because we flip it around, right? If the bigger one diverges, then we can't say anything about the smaller one. Can't say that. B of n is now the smaller one. A of n is the bigger one, so that's not that. So this is just just knowing your direct comparison test. Knowing how that works. That one would be B. All right, now we have a ton of examples that I think is just going to be helpful to do together. So I might split this up. I might just do them all at once. We'll see. But I'm already getting thirsty and I don't have any water. All right, so this one, it says compare. I'm going to see if it converges or diverges. So I'm going to compare it with, when I've got like polynomials on top and bottom, it's not just one. I'm going to compare it by the simplified version, so 1 over n cubed. And I'm going to do the limit comparison test here. Setting up a term-by-term comparison sounds like a nightmare. It might not be, but it doesn't sound fun to me. I like limit comparison test. So this thing is a p-series that converges because p is greater than 1. So I'm going to set my limit. My limit as n goes to infinity of the original one, and this could be flipped, it doesn't really matter, 3n plus 1 over 1 over n cubed. And I'm just looking at the limit. As long as it's positive and finite, this thing is going to also converge. That's my original one. 5n to the 5th plus 3n plus 1 times n cubed over 1. And I'm going to realize, okay, that would be multiplied by that. So the biggest thing, this would give me 2/5, which is a positive finite number. So my original series, I'm just going to say, I guess I'll write it out. This is going to behave the same way as the one I'm comparing it to. So since that thing converges, this thing converges by the limit comparison test. Do you need to write that this is positive and finite? I don't think so, as long as you show it. And then as long as you say that, as long as you say that this also converges, and how you know, you should be fine. All right, so this one looks pretty simple because there's nothing on top. I kind of want to just compare it to n equals 1. The series 1 over n squared, which is a p series. I don't know why I keep putting a dot after the p. P series that converges. And I could say pretty easily that this denominator is going to be bigger than this denominator every single time because I'm multiplying the n squared by 5, and then I'm adding things to that, right? And n is always going to be positive in this case. Greater than 1, 1 and greater. So I'm going to say 1 over 5n squared plus 5n plus 5 is less than or equal to 1 over n squared. If the denominator is bigger, the overall number is going to be smaller. For n greater than or equal to 1, because that's what I'm working with. I'm not working at negative n's because that would affect it and I couldn't say it. But for n greater than or equal to 1, that term by term relationship is going to work for sure. So my series that I'm trying to show, I'm going to write it all out again. So the bigger one converged, so this one's going to converge by the direct comparison test. All right. I'm going to run through these a little bit faster. I'm going to try not to talk. I'm just going to write them out. Okay, I know this is going to be like the next step, so I'll kind of take a little shortcut here. I think we'd be fine if we multiply by the reciprocal there and skip that first step, but maybe we should write out that first step that we're comparing the quotient of the limits we're comparing to.
Listeners.
So again, whatever you decide to compare it to, if I know this thing diverges, then this diverges if the limit of their quotients gives you a positive finite number. So if this thing the one I compared it to would have converged, then so would the one I'm comparing it with. That would also converge if I get a positive finite number. So that's it for this video. If you have any questions next time I see you in class, make sure you ask, and thank you for watching. Bye.